Hey friends, if you're needing some good news right now, Psalm 103 has some. First, we can't possibly fathom how much God loves us. That's going to be a pleasant surprise to find out. Second, if we ask Him to, God will take away our sins from us so far that no one will ever think of them again. In fact, they don't even exist anymore. That's great news. This lesson is going to be over material partly, but not fully covered in sections 3.4 and 3.5. It's a topic called curve fitting. The materials are posted in the notes worksheets folder. The note packet for this video is section 3534, curve fitting part 1, and there will be a part 2 later, and also using an Excel spreadsheet 3.4 deer population. So first, remember that chapter 3 is entitled Empirical Modeling. And the context is that this is a method of last resort. When we have no way to rely on theory or prior experience to help us choose the form of a model, then we sort of give up and black box it and just say, let me find something that works reasonably well, even if I don't understand why it works. I encourage you not to do that on your project. Try to find ways to build models that can be justified and explained, if at all possible. So there will be two parts here. This one is going to cover high-degree polynomial models and fitting linearized models to data. Then there will be a part 2 that will fit nonlinear models to data. So first, let's look at a really simple data set. 0, 3, 3, 4, 4, 11. Plotted here, 3 data points. And we might think about the simplest thing that we could do here, fitting a line to this. So I did it in Excel, and here is a linear model for the data, and the R squared is about 0.595. So not a terrible model, not a great model. If I look at the data more closely, I notice that based on this very limited evidence, only 3 points, but it looks concave up. And so I might decide, well, lines don't curve, but higher degree polynomials do. So how about if I decide to try and fit a parabola to these 3 data points? So here they are, and a parabola, as I just showed, uses not only the independent variable x, but also its square. And so how about we insert an additional column of data, which are the squares of the first column. And now my goal is to use both x and x squared to predict y. Well, I could flip back to the data sheet for a moment, worksheet for a moment. Now I'm really asking Excel to do a linear regression model. My 2 independent variables are x and x squared. It's true that these are related, but Excel doesn't have to know that. It just thinks it's getting 2 independent variables and it's supposed to fit a linear model to them. So let's ask it to do that. If I run data analysis and choose regression, and for my y range, give it the y values. Let's see, that went the wrong slot. For my y range, give it the y values. For my x range, drag through both the x and the x squared columns. Keep the labels box checked and ask Excel to do that. And it put the data table here, which is back on the notes. So I'm particularly interested, remember, in what's happening right here. And if I unpack those numbers and put it back in the context of the problem, here is my parabolic model. The R squared is interesting. It says 1. Well, that means that the model is perfect. And so I can explain why if I go ahead and graph this data again and superimpose the parabolic model on top of it. In fact, the model goes through all 3 data points, so there is no error for any of the data points. And so the model explains everything. It may have occurred to you that we could have done this problem another way. If I choose, well, let's just plot the data actually. Here is the original data. And if I generate a scatter plot and then ask Excel to add a trend line, but instead of having it do a linear fit, let's have it do a polynomial fit. And here in the order section, I can adjust this for what degree of polynomial I wanted to use. I chose 2 here since I'm talking about a parabola. And then let's have Excel display the equation on the chart and the R squared on the chart while we're at it. And there is the result from before. So Excel has this actually built in as one of its fitting options. Well, let's look at another example. Here are 11 black data points. And I decide, hey, I had so much success in the previous example at fitting a higher degree polynomial that how about we do that again? Notice up here that I had 3 data points and I used a second degree polynomial because a second degree polynomial actually has 3 coefficients if we include the constant. And if I have 3 coefficients to adjust, I'll be able to exactly go through 3 data points. So if I want to go through all of these black data points with a polynomial, how about we use a 10th degree polynomial, because a 10th degree polynomial has 11 coefficients counting the constant, and 11 coefficients, adjusting 11 coefficients will let me go through 11 data points. So that in fact has been done, and that's the blue graph, the 11th degree polynomial, which I'm not even going to give the coefficients here, but it has been done and it goes through all of the data points, and therefore the R squared is exactly equal to 1 and telling me that I have a perfect model. And all sounds good at the moment. Maybe you think, well, now we have it. We've finally arrived at the ultimate modeling technique. Regardless of which data set you get, just choose a high enough degree polynomial and it'll be able to go through all of the data points. You have a perfect model and end of story. But look at this. Is this really a good model? If all you had were the black data points, do you think that there's evidence that in between these 2 points that the actual values would go spiking high there, and that they'd drop down here and so on? There's no evidence to suggest that. In fact, if you had the black data points, wouldn't you expect a good model to look more like this orange curve rather than the blue polynomial? So is this polynomial a good model? No, it's terrible. It has oscillations. And if you think about it, polynomials are good at oscillating. A quadratic just has 1 minimum, but a 3rd degree polynomial, 4th degree polynomial, 5th degree polynomial, they can go up and down more and more, and very high degree polynomials can go up and down all over the place. It's sort of a polynomial's job to oscillate. And these oscillations between data points are non-desirable, that they're spurious. The real data probably doesn't do that, and they're unavoidable. If I fit a model in this way, there's no way that I can stop these wild between point oscillations from going on, especially near the endpoints of the data set, as you see here. So for practical purposes, high degree polynomial modeling is really a bad idea. And that also tells us that just relying on the r squared is not a good idea. Just because r squared equals 1 doesn't mean that the model is necessarily a good fit. You better look at a graph in addition to looking at r squared. There is one situation in which you might do this. This is called interpolation, by the way, when I force the curve to actually go through each data point. And if I'm doing computer graphics, for example, rendering special curves or fancy script lettering or something like that, I may want to do exactly that and force the curve to go through specified points. But that's different. That's a different topic than mathematical modeling and fitting to data. So let's abandon high degree polynomials, but let's try and keep this idea of linearized regression. By that I mean that if I treat both x and x squared as independent variables, then I can use linear regression, multiple linear regression, to fit parabolas. Now let's look at another data set. This is in the Excel file 3.4 deer population. So if I graph the data, and let's get that started, the years, notice, go from 1941 to 1982. We've already talked about that may not be the best scale. So what I'm going to do is scale the years, and let's go in years since, say, 1940. That will get the X values down in decent size. And then let's take a look at the data. And we see an effect like this. So now I could go one of several ways. First of all, this is a deer population over time, by the way. There seems to be definitely an overall downward trend, and in fact, maybe a linear trend. So it's not at all out of the question to think I'm just going to fit a line to this data, and that might be good enough. Might be what I want to do, but I also see something else. Notice that the data points, if I start here, it goes up and then down, and then up and then down, and then up and then down, and then up and then down. This is not entirely random, or probably not. And in real life examples, there might be reasons for this. There might be some sort of seasonal trends going on where the weather is good for a while and then bad for a while. Or it might just be that the deer are kind of dumb and they overeat. And so if there's a limited supply of grass, the deer overeat, and then there's not enough grass for everybody and the population goes down. But when it goes down, then there's not as much grass eaten, so it comes back, and then they can support more deer and the population goes up, and so on. And oscillations like that are sometimes observed in real biological populations. So I might say, well, I want to take this one more level and see if I can follow not just the downward trend overall, but a little bit of this bounce back and forth. And so don't worry at the moment how we decided to pick this particular form. We'll talk about that next time. But I'm going to fit both a linear part and then a trig part as well, with a cosine term and a sine term, and the model is supposed to put the most appropriate coefficients in front of those. And this pi x over 5 has to do with the period of these up and down oscillations, and we will talk about that again more next time. So if I were going to push this a little farther, I'll get the graph out of the way for the moment. I'm going to push this a little farther. Then the independent variables for this model are going to be, there are going to be 3 of them. One of them is the time itself. Another is pi times x divided by 5, take the cosine of that. And a third is same thing, but take the sine of that. So I'm just making label columns here to help me remember. And now let's actually do it. So here is cosine of pi, and I need empty parentheses. It's actually going to call a function called pi and return the value. Then times the time and divided by 5. And copy that formula down. Then let's do the same thing for sine. I times the time value divided by 5. And copy that down as well. So now the goal is to model the population as a function of x and the cosine and sine components. So it's multiple linear regression. Go back to our data analysis, choose regression, and for our y range, our dependent variable are the population numbers. For our x range, the independent variables are these 3 columns. Choose data labels, and I'll put the output in a new tab. I guess in the same tab actually. So here it is, and it's back on the notes packet, or I guess it isn't. Actually, where it is back in tab 2 of the spreadsheet where this completed model is there if you want to refer to. So let's look at what's going on here. Excel has completed a model, and there are the coefficients here. That is back on the note packet. I've taken those and unpacked them and put them back into mathematical form. So here is the form of the model that Excel found, and it reports that the R squared is 0.877. Let's go ahead and add a graph to this. So if I come back here, let's generate a column of predicted values. Okay, and I might copy my coefficients to empty cells, but I'm just going to go ahead and type the numbers here for sake of simplicity. So it was 19.279 minus 314.2 times the x value minus 2892 times the cosine term, and then minus 5704 times the sine term, like this, and drag down. Okay, now let's try and add the predicted values to a graph and see if we can show how good this is doing. So if I highlight my times and control drag through my populations and insert a graph of the actual data here, we downsize that a bit. Maybe I'll put it down below here. Or here. Okay. And then let's go ahead and add a series to that. So the new series can be named predicted values with its X components coming from, let's see, I think I want just this, and its Y values coming from here. And let's add that. So here is our graph. You can see that the blue values were the original population. The orange values are the new predictions. Now let me flip over to my completed sheet just to show a model, a graph that has more bells and whistles added. So I've changed the color and added had it connect the dots on the predicted model so we can see better. And this is not too bad, right? There is definitely an overall trend downward in the model like there was in the original data. And there is also a step up, down, up, down, up, down, up, down, and so on. In the completed spreadsheet here, I went ahead just as a reminder and computed the R squared by hand. So here are the predicted values, and then remember for R squared, you have to go through quite a series of computations, computing Y minus Y bar, Y minus Y hat minus Y bar, squaring each of those quantities. So JH and JK and L are squares of columns GH and I. And then SS total, SS residual, and SS regression are here as the sum of the respective squares in these columns. And finally, R squared is SS regression divided by SS total is 0.877, and that's what Excel told us when it did the linear regression. So was this good? Well, depends at what level you're trying to model. You may or may not in modeling want to try and closely fit to data. If you're looking for an overall trend and you think that the up and down business is more or less random accident, then it's probably not good to try and follow each little change in the actual data. But if you think there is a real seasonal trend here and you want to try and follow it, here's one way of doing that. And we'll stop there.